Welcome to the Explainer. I am absolutely thrilled you're here today because we are embarking on a true deep dive masterclass. We're calling this session the Sculptor, and it is going to be your ultimate Cambridge Physics exam strategy guide. Now, I want you to think about a master sculptor for a second. They start with this massive, unrefined, chaotic block of clay or marble, right? Our goal today is to take your raw block of physics ideas, carefully chip away all the irrelevant material, and reveal the absolute masterpiece of an answer that Cambridge examiners are literally desperate to see on your paper. We are going to specifically focus on the notoriously tricky topic of thermal convection in fluids under the Cambridge IGCSE Physics 0625 syllabus. But let me be very clear right out of the gate. The master strategies we unpack today are equally life-saving for syllabus codes 0651, 0652, 5054, and 9702. The physics might slightly vary in depth, but the strategy is universal. To set the stage here, I want you to visualize two students sitting down to take this exact exam. Let's call them Alex and Sam. Now, Alex is what we call the overloader. When faced with a past paper question on convection, Alex's brain just hits the panic button. They start writing down every single raw physics fact they have ever memorized since day one of class. It's just tons of facts, absolutely zero analytical structure. It's a brain dump. Then, on the other hand, there's Sam. Sam is the rusher. Sam completely misses the specific command word requirements of the question, words like explain or describe or evaluate, and just gives a superficial, rushed, one-sentence answer that barely scratches the surface of the physics involved. If we were looking at a dynamic split screen of their papers right now, you would just see a sea of red pen marks, red everywhere. They are both losing critical, grade-defining marks. And the tragedy is, it's not because they don't know the science. It's because they don't know how to sculpt the answer. Today, right here, right now, we fix that. So let's dive right in and look at the stakes. Take a look at that highlighted 15%. That is not just some random number pulled out of thin air. Did you know that thermal convection, and I mean specifically understanding it as a method of thermal energy transfer in liquids and gases, explicitly explaining it in terms of density changes, and knowing the core experiments to illustrate it, accounts for approximately 15% of the total marks in your Physics 0625 examination? I really want to let that sink in for a second. 15%. That is the difference between an A star and a B. Your entire grade could literally hinge on this one focused cluster of concepts. If you're currently acting like an Alex or a Sam in your mock exams, that 15% is just slipping right through your fingers into the abyss. But what's really exciting here is the opportunity it represents. Mastering this doesn't just mean robotic memorization of the definition of convection. It means understanding exactly what the senior examiners are hunting for when they scan your paper with their red pen. We are going to turn that 15% from a massive source of anxiety into an absolute stronghold for your final grade. By the time we're done, you're going to be looking for these questions because you'll know exactly how to crush them. Okay, here is our roadmap for today's explainer. First up, we'll tackle the convection concept. Second, we move into the technical methodology. Third, we uncover the top examiner warnings. And finally, we bring it all together with the master strategy. Let's get moving. Section 1. The convection concept. This is where we lay the bedrock foundation. Right, here is the absolute core definition we need to work with, and you need this hardwired into your brain. Convection is a method of thermal energy transfer specifically in liquids and gases, and, listen to this next part carefully, it must be explained in terms of density changes. Now, this brilliantly illustrates where students like Alex and Sam go completely off the rails. Alex sees the word convection and proceeds to write an epic, chaotic essay about heat moving, boiling water on a stove, and random particle theory, completely forgetting to ever mention the magic phrase, density changes. The examiner is looking for it, and it's just not there. Sam, our rusher, just scribbles heat goes up and moves on to the next page. Obviously, neither gets full marks. So, how do we fix this? To guarantee those marks, top students use the PEEL framework. That stands for point, evidence, explanation, link. Your point is clearly stating that thermal energy is transferring. Your evidence, or in the context of physics, your physical mechanism, is the specific liquids or gases being heated in the scenario. Your explanation, the most important part, is detailing that heating causes thermal expansion, which increases volume, therefore lowering the density, causing that warmer, less dense fluid to rise while the cooler, denser fluid sinks. And finally, your link ties it all back to the specific context of the question, like a radiator heating a bedroom. Before we continue,
Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Now that you're subscribed, let's put your brain to work. Here is a highly effective memory hack pulled straight from our research into how top-tier students study. I have a live challenge for you, right now, wherever you're watching this. I want you to create your own mnemonic using the first letters of the key convection terms we just discussed: liquid, gas, thermal, density, transfer. Just think about it for a second. L, G, T, D, T. Maybe something like, let gases transfer thermal density? Or if you want to get a bit weirder with it so it sticks, little green turtles demand tomatoes? Honestly, whatever works for your unique brain. The conceptual framework for convection relies on these established principles, and creating a personalized memory device ensures that under the high-pressure, sweaty palms environment of the exam hall, you don't accidentally leave out that absolutely crucial element of density. When the exam timer is ruthlessly ticking down, having that mnemonic locked in your mind acts like an anchor. It completely prevents the panicked, unstructured brain dump that Alex struggles with. It gives you a checklist right there in your head.
But look, knowing the definition and having a mnemonic is really only level 1 of the game. The principal examiner reports, which are basically the cheat codes for these exams, consistently highlight a fascinating trend year after year. The candidates who achieve significantly higher marks, the ones pulling those top grades, they don't just regurgitate the definition of convection in isolation. They actively make cross-topic connections. The theoretical architecture of convection rests on deep causal relationships and integration with other syllabus areas. For example, can you connect the macro idea of convection to the micro world of the particle model of matter? Can you relate those specific density changes to the kinetic energy of the individual molecules pushing further apart? The Cambridge assessment framework heavily prioritizes this kind of analytical depth over superficial breadth. You have to stop treating chapters in your textbook as separate, isolated islands. They are all connected, and showing the examiner you see those connections is how you sculpt a masterpiece. Moving right along to Section 2, Technical Methodology. This is where theory meets practice. Okay, pay close attention, because this is the absolute core of your procedural framework. Practical application in Cambridge physics requires professional-level skills, and data interpretation is critical. You absolutely must be able to extract data from complex texts and tables, interpret the relationships between those variables, and draw solid evidence-based conclusions. Let's do an interactive workshop right now. Imagine we have a 60-second visual timer running on the screen, ticking down. Tick-tock. I put a complex chart showing temperature gradients and fluid dynamics right in front of you. This is our data scan challenge. In those 60 seconds, a top-tier student isn't just blankly staring at the numbers. They are immediately scanning for the core trend. Is the temperature change linear? Does it directly correlate with a calculated density change? Remember our students from the beginning? If we took Alex and Sam's flawed, red ink-covered answers right now and put them through a live rewrite guided by these exact data interpretation skills, you would see a literal transformation on the page. Those red pen marks would transform into beautiful green check marks. Why? Because instead of Sam just vaguely stating, the water got hot, Sam would extract the exact starting and ending temperatures from the table, interpret that the massive increase in kinetic energy led to volume expansion, and conclude that this specific mathematical density change drove the convection current shown in the experiment. That is the depth that earns the marks. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, welcome back. To execute that level of depth consistently, every single time, you need a flawless system. I like to call this the physics success blueprint, but formally in the educational world, it's known as the deconstruct, solve, evaluate framework. Let's break it down. First, identify the given info. Literally highlight the numbers, the types of fluids, the environmental conditions in the prompt. Second, break it into logical steps. Don't just blindly jump to the end answer. Map the journey your logic will take. Third, solve systematically using your core physics principles and formulas. Fourth, and this is massive, check for reasonableness. Look, if you calculate that the convection current is moving at the speed of sound in a tiny glass beaker of water, you've made a math mistake. Catch it before the examiner does. Finally, step 5, make justified recommendations or conclusions based entirely on the evidence you just laid out. The higher order assessment objectives in Cambridge exams demand this kind of evaluation and comparison. You are proving to them that you think like a physicist. Let's jump into Section 3, Top Examiner Warnings. This is where we look at the traps so you can avoid them. Urgently, I need you to internalize these top 3 student mistakes straight from the examiner reports. 1. Forgetting to include proper format. 2. Forgetting to check that format in presentation before moving on. 3. Providing answers that are completely general and not specific to the given context. Let's play a quick interactive game of Find the Flaw. Imagine our rusher Sam writes this exact paragraph for a 6-mark question. Convection is when heat transfers in liquids. The liquid gets hot and rises. This happens in the experiment. All right, look at it. Where is the massive flaw there? According to our examiner warnings, it's point number 3 screaming at us. It is not specific to the context. What liquid? What specific experiment? Is it water? Is it oil? Sam just easily lost 2 or 3 marks just by being vague. Presentation of information in physics follows strict conventions. You need proper headings if asked, correct terminology like thermal energy instead of just heat, appropriate formats, and clear annotation if you're drawing a diagram. If the exam question asks about a coastal sea breeze, your answer must specifically mention the land, the sea, the sun, and the specific heat capacities involved driving that exact convection current. General answers get generally poor grades. It's that simple. Now, here is a crucial grade-saving insight directly from the grading floor. Students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. Consider this a massive examiner alert. The method mark strategy is quite literally your best friend in the exam hall. Marks in Cambridge Physics are routinely awarded for the process, the logic, and the methodology, not just arriving at the final numerical destination. If you use that Peel framework we talked about, and you clearly lay out your data extraction step by step on the page, the examiner can see the gears turning in your logic. Even if you mess up a final calculation because you press the wrong button on your calculator, your clear, sculpted working out will catch those safety net method marks. Imagine a speed writing challenge right now. Let's say you have a 30-second timer counting down on the screen to write one perfect Peel paragraph explaining why a room heater is always placed near the floor. 30 seconds go. If you just rush and write the final answer, so the whole room gets warm, you risk everything. But if you show the method, the heating of the air molecules, the expansion, the volume increase, the density drop, the rising of the warmer air pushing cold air down to be heated, you secure all the method marks. You win the game by showing your work. Finally, we reach section 4, the master strategy. Let's bring all these pieces together into one cohesive system. What you are looking at right now is the ultimate systematic processing sequence that top-scoring, elite candidates use. Notice how all the theory, the methodology, and the warnings flow together into 3 overarching rules that essentially guarantee top marks if applied correctly. First rule, command word decoding. You must identify the key elements of the question and pair them with exactly what the command word is demanding. If the question says describe, it just means say what happens visibly. If it says explain, you have to say exactly why it happens, using underlying physics principles like density and kinetic energy. Second rule, Peel framework application. When you execute your analysis with clear, methodical working, your point, evidence, explanation, and link ensure your answer is incredibly robust and impossible to mark down. Third rule, the time management matrix. Verifying your results for reasonableness and presenting them in the appropriate format requires you to manage your time effectively, so you aren't rushing at the end like Sam or brain dumping for 20 minutes on a 2-mark question like Alex. Students who implement these specific physics strategies see an average improvement of 2 full grade boundaries. But, and this is a big but, that only happens if they practice consistently with our weekly explainer videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. As we wrap up this masterclass, I want to leave you with this final provocative thought to chew on during your next study session. Are you just blindly memorizing isolated facts like Alex, hoping they stick, or are you actively applying the deconstruct, solve, evaluate framework to your past papers? Real exam mastery, the kind that gets you the highest marks possible in Cambridge Physics, is not about how much raw data you can cram into your head the night before. It's entirely about how brilliantly you can sculpt that data into a specific, context-driven, beautifully formatted answer that makes the examiner's job easy. Drop a comment below with your target grade for physics and tell us the biggest challenge you're facing right now. Our team responds to every single comment, and we want to help you overcome it. Like and share this video with a study partner who needs to hear this. Ace the Exams. Your Cambridge success starts here. Thanks for joining this explainer, and I'll see you in the next one.